Today we're going to talk about, and we're going to give you an introduction to calculus. Lots of the applications of calculus will be done next year in relationship to science, engineering, physics, things like that, and also some calculus or some vectors will be included in there. Some things that we'll talk about and we'll introduce this year are the ideas of limits, and we'll also get into a little bit of differential and integral calculus, at least introduce what those are, and the fundamental theorem of calculus will come next year as well. So we're going to give you an introduction to calculus. Before we do that, we need to talk about continuity. A function is continuous on an interval if it is continuous for each value of x in that interval. So what does that mean? It means it has no asymptotes. It's continuous through all points. There are different types of continuity. Discontinuity, infinite discontinuity has your asymptotes. Jump discontinuity is typically with your piecewise functions or step functions, and then point discontinuity will have holes. So it might be a situation where it's not an asymptote, but just a hole in the function. And we'll take a look at those as well. So on to limits. Limits are the basis of derivatives. And you've done a little bit of work, or we've done some previous work with the power rule of derivatives to find certain things with polynomials, but the limit is essential to calculus, especially differential calculus. We first introduced the idea of derivatives using limits. So what we're looking at here is consider this following table. So I have a table here of x values as x is getting closer and closer to 2. 2 would be theoretically right there. What's happening to the function as the x values get closer and closer to 2? You'll notice that they also get closer and closer. The function itself gets closer and closer to 4. So that's what is considered its limit. And we write it in this form. The limit of x squared as x approaches x approaches 2 is 4. That's how you would read that. The limit of x squared as x approaches 2 is 4. Now, this is what we call a definite limit. And if we remember, this function looks something like this. And if 2 is over here, there's the point 4. As I move along this curve, I'm getting closer and closer to 4. And as I move along this curve, I'm coming down here, I'm getting closer and closer to 4. That's its limit. At that specific point, the function is equal to 4. The informal definition of a limit, when x approaches some value, limit of a function as x approaches some value is equal to some other value. It's converging to a specific value. So when we get into other functions, now this is polynomial functions are relatively easy, but when you get to functions like this, where if we say we're approaching 0, I obviously can't put 0 in there because then it would be undefined. We can't divide by 0. It's tempting to do, but we cannot do that. So what we have to do is we have to observe the two parts to the function. There are really two parts to this function, because I could separate this out. I could say, all right, x is undefined at 0, but I can also take 5x divided by x plus x squared divided by x and get a second function, which is 5 plus x, which therefore gives us a line. And that's what we're seeing in this graph. As I move along this graph, as I approach 0 from both directions, I'm noticing that it approaches that specific value of y equals 5. And that is what our limit is. A limit is the y value of whatever this is approaching at a certain point. It's really just the y value. Now that's an informal definition of a limit. We'll get to a more formal definition of a limit next year. Here's the same types of problems. So definite limits. Okay? We can find the definite limit. We simply plug 2 into the function x squared. When x approaches 2, I put 2 squared, the limit of x squared as x approaches 2. I put 2 in there, and therefore the limit is 4. Over here, I'd have to separate that out like I previously showed, but the limit as x approaches 0 of 5x plus x squared over x is 5. And the only way we can do it, we can't put 0 in to get that. If I put 0 in, I don't get an answer. It's undefined. And that's why I have to separate it out, calculate it otherwise, but x is not equal 0. Okay. Continuing, there are some rules for limits. This is the limit of a constant value, no matter what it approaches. Constant value, it's going to equal that value. So, example, what that means is if the function looks like this, and that's 3, as it approaches this value, as x approaches -3, what's its value? No matter what it's doing, its y value is 3, because that's what it's equal to. That's its constant. Okay? The limit of a constant times a function is equal to the constant times the limit of the given function, and so on. And you see adding limits and so on. We'll get more into those theorems and those formulas later. Rules to evaluate limits, you just plug the values in. Now I could FOIL this out and do it that way. You can just plug the values in. So for a, it's simply the limit as x approaches 3 of x plus 2 and x minus 1. I simply plug the 3 in. So that's 3 plus 2 times 3 minus 1. So that's 5 times 2, which is 10. So it has a limit of 10. And similarly, I would do that with problem B, plugging 1 in. So the limit of x squared plus 2 divided by x minus 2, if I put 1 in there, as x approaches 1, put 1 into the problem, I get 1 squared plus 2 over 1 minus 2, which is 3 over -1, so the limit is -3. It's that simple. Right? So those are limits. Now, sometimes we do limits to infinity, as the function goes off to infinity. And that's a little bit different. Now, infinity is not a number. It is an idea. We can't name a number that's infinity. Infinity is not a number. It's a concept. But what we do is we can identify, according to rational functions, if I have the rational function 1 over x, I have the rational function 1 over x. If x approaches infinity, I take 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 10, 1 divided by 100, 1 divided by 1,000 or 1,000,000 or whatever it is, 10,000 in this case. What is happening to the value of the function? It's getting closer and closer to 0. It's approaching 0. So that's really what a limit is. It's a value that a function is approaching. Is it ever going to reach that? No, but it's going to get extremely close and therefore become 0 to infinity. When we go to infinity, it becomes 0. I'm not dividing by 0. I'm simply taking 1 divided by an extremely large number, 1,000,000, 1,000,000,000, 1,000,000,000,000, and then the closer that gets to 0. Same thing if I have x over x squared, because what can I do with x over x squared? Isn't this x over x times x, and I can cancel one of those out, so really it's just 1 over x again, therefore its limit is also 0. Okay. And we use that idea to do limits to infinity. Now, to infinity for any problem, what you're going to do is divide. This is a simple trick, an informal trick of doing limits. We'll do the formal part next year. The informal trick of doing limits is simply dividing all parts of the function by the largest power of x from the denominator. So in this problem, there's a power of x to the first in the denominator. I'm going to divide everything in the function by that. So the limit as x approaches infinity is equal to 2x divided by x plus 3 divided by x over x divided by x minus 4 divided by x. And we can simplify that. Well, 2x divided by x is just 2 plus. Well, what's 3 divided by a very large number? No matter what, if I go to a million, billion, trillion, it's just going to be 0. It's approaching 0. As I put x to infinity, it becomes 0. On the bottom, what's x divided by x? 1. Minus, what's 4 divided by infinity? 4 divided by anything large is going to eventually become 0. It's insignificant. So my answer is 2. The limit of this function is 2. We can do the same similarly for another problem. Again, I would divide, because it's going to infinity. I can only do this with limits that go to infinity. I would simply divide everything by the largest power of x in the denominator. So the largest power of x in the denominator is x squared. So the limit as x approaches infinity is equal to x squared over x squared minus 3x over x squared plus 2 over x squared over 1 over x squared minus x squared over x squared. Well, we can simplify that. X squared divided by x squared is 1 minus, 3x divided by x squared. I cancel out the x on top with the x on, what's 3 divided by x? I'll put that over here. 3 divided by infinity is approaching 0. It becomes insignificant, as does the 2 divided by x squared. It just happens faster. And then on the bottom, 1 divided by x squared is 0 minus x squared divided by x squared is 1. So really I have 1 over negative 1, so my limit is negative 1. Some very simple rules or simple concepts of limits that we introduced this year. We will do more with limits in the future. In the beginning of next year when we do derivatives and expand on the concept of a limit. We're going to use them in this unit, find asymptotes and things like that.